Section 5.1, Approximating and Computing Area. In this section, I will actually try to introduce a second branch of calculus, which is called integral calculus. Yeah, let's look at this quick description. We did talk a lot about the differential calculus, of course, lots of rules of differentiation. Differential calculus mainly focus on finding the instantaneous rate of change. And for instance, slope of the tangent line is it's the instantaneous rate of change, the change of the function at the given point. Also, we remember the way that we found the tangent, slope of the tangent line. We use the limiting process, the limit process, the fundamental concept of calculus. Using slope of the secant line, and the limiting position of the slope of the secant line was the tangent line. Yes, and we use specific limit, and then we got the limit definition of the derivative. Also, velocity problem, it's almost the same problem, finding the velocity at that instant, the rate of change of distance with respect to time. It's also the derivative concept, or actually finding any instantaneous rate of change. We will talk about the derivatives. That meaning that when we have a function, we will differentiate function. Now, taking that rate of change, taking that derivative, we will try to recover the original function, original amount, original distance, and that will be the process of integration. Or we can actually say a little bit more directly, integration means anti-differentiation. We will reverse differentiation. And the theorem that is connecting both of them, differential and integral calculus, is called fundamental theorem of calculus. I mean, that's how we will finalize this chapter. But let's first introduce. We will start with some approximation like we did for the tangent line. That means even if this looks opposite operation, mathematical operation, they have lots of in common. Okay, that's what we can do. First of all, let's maybe check if we understand integration. That means, for instance, when I will say that I am driving and my velocity, my speed, let's say velocity is 50 miles per hour. Yeah. Then if I will ask you, what will be my distance? What will be my distance after 1 hour? Yeah. You will tell me 50 miles. Yeah. Let's say after 1. After 2 hours will be 100 miles. And so on. So now we can see we did recover the value of the original function, distance, position function. That means actually we know the calculus. I mean, we know the integration calculus. From the rate of change, we did recover original amount. Okay, that's actually calculus. Why I am saying calculus? That's actually integration calculus. Okay, but let's see. Everything it's not as smooth and straight as we will wish. That means this is velocity, this is time. And I just mentioned that my velocity, my speed was 50. That's mean, okay, 50, and after 1 hour, I drove 50 miles. After 2 hours, I drove another 50, 100. But now the main question is, when I'm driving or when you're driving, do you think always the speed is exactly like, it's constant, it's always like 50 miles per hour? Of course not. I could drive a little bit faster and maybe a little bit slower and then faster. And then what is my distance after 3 hours? What is my distance after 4 hours of my drive? 5 hours, and so on. Yeah, that's when we can see it's not as simple. But if we think about this constant and we've got 50 miles, 100 miles, we basically found the area under the velocity. That means 50 times 1 is 50. Right? And then 50 times, 1, or in general, I can say 50 times 2. Just the area of the region under the rate of change, under the velocity curve, will give us the amount of the miles. That means we'll recover in some way the original function, information about the original function. But now, since I'm not driving like with the constant velocity, like what is that area? Yes, if one side in this case is not like straight, what is this area? Because this area will tell me amount of miles. And this is the introduction to this integral calculus. We have to find out what is the area under the curve, and the curve is not a straight line. Then this will be in some way the definition of the integral. Okay, antiderivative. Okay, that means let's focus on, probably we will try to approximate like we did the slope of the tangent, but we will make the approximation as perfect as possible. Okay, with almost zero like mistake. And this will be my number of miles, amount of miles traveled. That's, we have to find out the area. Okay, that means, and we know why. We know why, because we need that to recover the amount of the miles. Okay, so now, in general, because finding that area, this is mathematically, like theoretically, that's the tool, that will be called integration at some point in chapter 5. But what we're doing in general, from the rate of change of the distance with respect to time, from the rate of change, we recover an original function, the value of the function, but we're recovering the original function. That's mean we kind of like anti-differentiating. And this process, it's extremely important, and we have lots of application. We will need this, I just named a couple of them, like how from the rate of change, from the derivative, we can recover the original amount. Yeah, like distance traveled by the object, that's what we just discussed. Yeah? Having the velocity, how we can find the distance. Then length of the curve, volumes of the solid, center of the mass, force due to the water pressure, for instance, work, consumer surplus, producer surplus, and any other like finance like quantities. That means all of these, and we have more of these applications that we will actually use. This is actually my 50. We will use this like anti-differentiation process from the rate of change. Yes, we will try to recover these values. Okay, and we know that this concept will lead us, at least at the moment, to finding the area under irregular curve. Okay, so now the area problem. We have to try to figure out. The area problem is not a problem if all of the sides are straight. Let's see, rectangles, triangles, polygons. All of the sides are straight. We know the area of the rectangle, length times width, triangle, 1/2 base times height. Any polygon I can divide by triangles and find the area of each of them. That means that's not a problem. The problem begins, for instance, if I will look at this question. What is the area under x squared between 0 and 1 and above the x-axis? We may say it's a little bit less than half of this square 1 by 1. Yeah, or the triangle, but it will be still a big approximation with a big error. That's, we have to do a little bit better. You may pause the video and think about the ideas. Okay, I mean, what we will do? We will try something like this. Okay, now. Okay, we have the same thing, the same function, x squared on the interval from 0 to 1. And what I will do, I will divide this area, this region. I will use the vertical lines, and I will create, like in this case, I just decided to use 4 because we can see 4 like stripes. Right? That means n is 4. I did divide equally because that's what we will do. The interval from 0 to 1, I divided by 4. That means it will be 1/4, 1/4, 1/4, another 4, of course, 4 quarters. That's when I'm drawing these vertical lines, creating this stripes. And actually, I can also do this on this side. Okay, but now and it's still the top of each stripe is a curve. It's not a straight line. That's what I will do. I will try to create rectangles, okay? And we will have a couple of ways to create the rectangles because the rectangle needs a base and a height. Base will be that distance, okay? That's 1/4, 1/4. We can see this is the base, 1/4, 1/4, 1/4, 2/4, which is 1/2, 3/4, and 4/4. Okay? And we will call this base that I divided the entire interval, we will call delta x. Okay? Delta x is the entire interval from a to b divided by n. 1/4 in this case. A and b is the beginning and end. Yeah, the entire length divided by number of rectangles. And now we can create the rectangles, as I said, and we will have two ways, right endpoints and the left endpoints. And let's see. Looking at the first subinterval between 0 and 1/4, I will use, okay, this will be A, the right-hand side. The right-hand side endpoints. From 0 to 1/4, 1/4, that value of the function will give me the height. That means I will build the rectangle. And then again, between 1/4 and 1/2, 1/2 is on the right-hand side. This will give me the height. Between 1/2 and 3/4, 3/4 is on the right-hand side, and this will give me the height. The last subinterval, 1 is on the right-hand side, 1 will be the height. And then I have to find the area of these rectangles, easy. We have the height, we have the base, just 4 of them adding together, and that will be the approximation. We can still see it's not perfect because the rectangles are sticking out, the yellow, the golden region, but it's at least something. Okay, or I can use the left-hand side. Okay, now let's see. Between 0 and 1/4, that's the first stripe or first subinterval, 0 is on the left-hand side. And 0 will give me the height, which is actually 0. Between 1/4 and 1/2, 1/4 is on the left-hand side, and this will give me the height, the value of the function for 1/4. And then 1/2 and 3/4, 1/2 is on the right-hand side, on the left-hand side, and this will give me the height. 3/4 and 1, 3/4 is on the left-hand side, and this will give me the height. Okay. As we can see, it's still not a perfect because I'm missing, they are way too low. I am missing this, but as I said, at least we have something. I can compute the right-hand side, I can compute the left-hand side, and maybe take the average. It will be not bad. Okay, let's see the calculation. The right-hand side, the left-hand side, and now base, we can see 1/4, times the height, and height is the value of the function. Function was defined as a x squared. That means we're squaring 1/2, we're squaring, 1/4, 1/2, 3/4, 1. Then we're squaring 0, we're squaring 1/4, 1/2, and 3/4. Okay, that's what we can see. And this is just basically delta x times the value of the function for the certain point. Let's say x sub a. And that means the area is just base times height of each rectangle. Base is delta x and height is the value of the function for the certain sample points. This one, this one, this one. This one is on the right-hand side, this one on the left. Okay, and when we do the math at everything, it will be 0.46, 0.21, 22, and we know that definitely the area is between. Okay. As we can see, this is the method, and we will use that method. We will definitely use this method. One thing that I would like to mention, this one is overestimated. Okay, one thing that I would like to mention, we will probably focus on the left, and the right-hand side and the left-hand side only, even on the right-hand side a little bit more, right? The right endpoints and the left endpoints. But just in general, please note that we may actually pick any point. Sometimes depends on the curve. Like let's say I will pick the sample point here. I mean, this will be the height. Or maybe I will pick something in the middle. Then this will be the height. Let's say this will be the height. Yeah, we can see a little bit, that will be the height. Yeah, and this in the middle. That's we may have, and then I have to compute the middle points, for instance, get the height, base is the same, 1/4, and get the approximation. Yeah, I just want to tell you that we may have sample points, any sample point. This will be like, let's say, X star sample point. Yeah? X star, of course, X sub 1, X sub 2. That means just in general, but we will focus only on the left or right-hand side. Okay, but now, our problem, we overestimated, we underestimated. That's how we can improve, keeping that method, that tool, how we can improve this. Probably, and the same, you can pause the video and try to answer to yourself. Probably you will think that number of these rectangles, of these stripes is not enough. And that's actually true. We may use larger number of stripes. This is left, this is right-hand side. For instance, I use 8. I divided the interval from 0 to 1 by 8. And you can see, yes, you can definitely see it's much, much better because that empty, it's smaller, that's, yeah. And the approximation is a little bit better. 0.27, 0.39, a little bit closer. And you may even think even 8 is not enough. We can increase number of rectangles. And let's see this. I took 10, yeah, 30 right and left, 50 right and left. And we can see even 50, how we perfectly plotting almost like the top of these rectangles, creating our curve, x squared. Okay, that means this is the point. And we know that the approximation will be even better, perfect, if number of these stripes, number of these rectangles will be infinity. That's our point. We want n to go to the infinity. And this is notation, the right-hand side, yes, approximating the area by the right-hand side, for instance. And this is left-hand side of the height, the sample points, and n is number of rectangles, number of stripes. Okay, that's our point. We know the method at the moment, but we will see this. And we have to find out some short notation because I don't want to sit and add 50 areas. Yes, like the delta x, the base of this rectangle will be 1/50, 2/50, 3/50. That's sample points. 1/50 is delta x. Delta x. Oh, my pen is, I can use this. Delta x will be 1/50, but the sample points. And then we have to find the value of the function times 1/50 each and then add together. We have to figure out some shorter notation. Or 50 is maybe doable. What about infinity? Okay, but this is the method. And actually, let's look at the number, even 50. The right-hand side approximation, 0.34. The left-hand side, 0.32. That means we may probably guess, yes, that this approximation, let's look at this, that's number of rectangles, number of stripes, using left-hand side sample points to be the height of the rectangle, right-hand side, and I added like 10 of them, 20, 30, 50, 100, 1,000. Let's look at this, 0.33, 0.33. Approximate, yeah? The estimation is that that area is 1/3. That means ideally we'll be finding the general formula, the right-hand side or the left-hand side, but I will focus on the right-hand side. And that formula will depend on n, because n is like n, infinity, and we will evaluate this. And we will do this. We will finish the session with this exercise, okay? And we have to get 1/3. This 1/3 we just get numerically by approximating, okay? That's the way at the moment. Now let's look at the general. Yeah, that's we do have, yes, we do have this region. the curve f of x between A and B, and this is the golden region, and we have to find out the area. Okay? We will definitely divide by the this interval AB by sub-intervals, the stripes, and we want n of them. But let me look at the notes. Yeah, it's not easy. We have to do some approximation. That means we know that we will use this rectangles method. But even if this looks a little bit different at the moment, we also did the tangent line. We did like the secant line closer and closer and closer to the tangent. That means it's something similar, and we're getting more and more and more of these rectangles. That means the process is a little bit similar. But let's see, because we would like to focus on this. What I have, that's the region. I divided by stripes. That's the sample points, x sub 1, x sub 2, x sub 3. We can see this. And actually, I use the right-hand side. Yes, you can see between A and x sub 1 is on the right-hand side. That's the value, and that's the height, and so on. Delta x is the base. We know how to compute delta x. Delta x is quite important. Yeah, that's delta x, that's delta x. The entire interval, b minus a, the right minus left, dividing by n. That's n. Okay, important formula. Okay, so now, okay, we do have equal, yes, width. That means this is the width of the entire interval from a to b. It's b minus a. Now delta x, the base, the width of each stripe is b minus a over n. Important. Okay. And then the right-hand side endpoints, it will be f of x sub I. We will call x sub I, x sub 1, x sub 2, x sub 3, and so on. And then the area of this rectangle, let's say this one, each of them. The area is, of course, base times height. Base is delta x, and height is the value of the function for the sample point. Okay, now we have to figure out the sample points, because I cannot say f of x sub 1, f of x sub 2. We have to have more general information, because what we will know, we will definitely know A and B. A will be given, and B will be given. Beginning and end. Delta x, we can compute, because this will be this. And if n is a finite number, we can divide. If n is n, we have to keep it at the end, infinity. We will also keep this. Okay, but delta x will be available, because we can compute this. That means now, if this is distance a, then this distance will be a plus delta x. That means that x sub 1 can be evaluated as a plus delta x. Now, the second sample point will be a plus delta x plus another delta x. That means this point could be a plus 2 times delta x, and so on. A plus delta x, delta x, delta x. That means the third point could be a plus 3 times delta x. Then let's see, a plus delta x, a plus 2 times delta x, a plus 3 times delta x. Basically, x sub I in general will be a plus I times delta x. Okay, important. Delta x as a base of this rectangle and the sample point. And this is, of course, right-hand side, right endpoints, because you can see I use the right endpoints. Okay. We know this. Now, I can say that the area is basically base times height, base times height. This is sample points, but we have the formula in general. Okay? So now we can see we have this n, of course, goes to the infinity. So now let's see how we can rewrite this, like this. That area can be approximated by right-hand side endpoints, left-hand side endpoints, or maybe just the sample points. Do you remember I show you like some blue endpoint? But now let's see, we did add limit. We will have the formula base times height yeah, area of the rectangles, but we have infinitely many of them. That's mean the limit, and this is the first height times delta x, the second height times the base, and so, and the last one. But the last one, yeah, n is infinity. As soon as we get this formula, hopefully we can get nice formula. We can compute the limit. We know how to compute the limits, and we will have the area approximating. We will approximate the area, and we know how important is this process. I mean that number to approximate the area under the curve. Will recover the original function. It's anti-differentiation integration. Okay. Yeah, and we know all of these formulas, assuming that everything that we looking at, we're dealing with the continuous function. Okay, so now, one thing we may notice, as I said, I just have 1, 2, 3, 4, 5. If we have a lot of the rectangles, we don't want to write infinitely many of them. We do have a special notation for addition of similar terms. And this notation is called sigma notation. Okay, that's we can see. Let me show you the entire. Oh, okay. That means sigma notation means sigma. That symbol just means that we adding that formula. And this formula, you can see, we can repeat, but that index is changing from 1 to n. Yeah, that means everything else we will copy, but except I, except 1, except 2, except 3, 4, 5, n. N is the last one. Okay? It means now, I just wrote again, but we will focus on the right-hand side only. This represents the right-hand side because we're starting from, we can see from 1. Yes, the right-hand side, we will start from 1. This one, yeah, I minus 1, we're starting from like 0 from the left-hand side, and this is just random, just the sample. Yes, sample points, and it could be any point, we don't know. But we will focus on the right-hand side, since we know that delta x can be computed this way, important formula, and x sub I is a plus I times delta x. Okay. We still have to find this 1/3. And now what we will do, I can show you a couple of linearity, the properties of the sigma. When we have a summation of constant times the formula, that constant will stay and we will just focus on the formula. Summation of the addition is the addition of two summations. Summation of the difference is the difference of two summations. Also, we have a couple of formulas from algebra, probably from high school, when we adding just the counting numbers. Yeah? Summation of I means that I is changing from 1 to, oh, I suppose to put n, let's say. 1 plus 2 plus 3 plus 4 plus n. Okay, n could be infinity, but let's keep this one for calc. 2. Okay, that means now we're adding squares of the counting numbers. 1 squared plus 2 squared, 3 squared, and so on. And that's the cubes. And these formulas are just simply representing this. I will not prove. The first one is easy to prove because it's a nice story about the Carl Friedrich Gauss. The other two are a little bit more complicated, but you have to just trust me that this is correct. Okay, that's when we will, and let's see how we can use them. Okay, that's when, for instance, oh, that's the short story. I will skip this for a second. Okay, so now let's actually prove this. Okay, we know that we approximated, but if n is infinity, if we have infinitely many of these stripes, rectangles, the area will be 1/3. That means what I need, that R means that we're using right-hand side endpoints. And this is the formula, delta x. Yeah? Delta x is just the entire interval. Delta x is b minus a over n. B minus 1 minus 0 over n, 1 over n. Each base is 1 over n. That's delta x base. Now height is the value of the function. Function is x squared. That means I will square the first number, and we can see this will be 1 over n, this will be 2 over n, 3 over n, 4 over n, 5 over n, and so on. Yeah, that's that's actually the values, the endpoints, and I have it. The first number squared, the second number squared, and so on. And let's try to simplify this. We can definitely factor out 1 over n, 1 over n, 1 over n, 1 over n. That's this. Yeah, that's delta x. I did factor out. Now, each of the denominator will be n squared, n squared, n squared, n squared. I factor out, and on the top, we will have 1 squared plus 2 squared plus 3 squared plus n squared. And now, this is the moment to use the formula. Addition of the squared of the counting numbers. Okay, this is n cubed. That's the formula. Yeah, we remember one slide before. That means this is the moment that we're using this formula. And now this formula looks like this, and we just have to compute a limit. How this expression behaves as n goes to the infinity. You know, this is, you may pause the video and you may answer, okay, 2n times n, 2n squared versus 6n squared, 2 over 6, 1/3. 1/3. Yes, we prove it. That means it's quite long process, but this is the process of finding antiderivative, like, yeah, through the nice limit definition, I can say. We will put everything together in the next section, but this is the nice introduction. And I do have this question. Yeah, the same thing you can see is x squared, x cubed, complicated. I didn't draw this polynomial, but what is the area under the curve over interval from 0 to 4? Yeah, we have to compute this. Let's maybe do it because we will come. Yeah, I type this one. That's me. First of all, is this. Yeah? I use the sigma notation. Delta x times f of xi. Base times height, and we're adding all of them. We have from 1 to n is infinity. So now let's see, delta x in this situation will be b minus a over n, 4 minus 0 over n, 4 over n. So we can see we have this. And now x sub I was defined as a plus I times delta x. A is the initial point, 0 plus I times 4 over n. That means x sub I is 4i over n. Now we know that that's the sample points. I copy the formula. But now instead of x sub I did put 4i over n. As we can see, 4i over n, 4i over n squared, 4i over n cubed. Let's evaluate. Summation, I mean, this is constant, yeah, because this is not changing. I is not present. That means I can put outside. Now, summation of the sum is the sum of all of these summations. That means sigma of 1, sigma of this, and this. We can see. Now, summation of 1 means that we will be adding 1 plus 1 plus 1 plus 1 n times. That means it will be basically 1 times n. Okay, this formula, only I, it's changing from 1 to n. 4 over n is not changing. 4 over n squared is not changing. 4 over n cubed is not changing. That means 4 over n outside, 16 over n squared outside, 64 over n cubed outside. Only I cubed stays, I squared, and I. Okay, and now it's the moment to use the formulas. This is just n. I copy 4 over n, and I means that we're adding 1. I is changing from 1 to n, 1 plus 2 plus 3 plus 4, but we have the formula. We remember 2 slides before. Now we need the formula for I squared. That's the formula, addition of the squared numbers, and that's the formula for I cube. Okay. Okay, and now we can see no sigma, no, we may look what this, that n will be cancel out. Oh, actually, no, first of all, let's don't cancel out. I mean, I could, but I think I multiply everything. I distribute this one. 4 over n times n is 4. 4 times 4 is 16, and I copy this, and n times n is n squared, and copy this. Now, I copy the entire numerator times 4, 64, and n times n is n cubed, 6n cubed, and this one. 64 times 4, 256, and then copy everything, and n cubed times n is n to the power of 4, and this is 4. And now we can see this is n squared, this is n squared, n cubed, n squared, n squared. That means all of the limits exist as a finite number, non-zero. This will be 16 over 2, 8. This will be 64 over 6, or actually times 2, then 64 over 3, because this will cancel out. 256 divided by 4, which is 64. Okay, and now we can add together. It's supposed to be 97 and 1/3. Okay, that means the area under the curve of this function between 0 and 4 is this, and this is perfect. It's a nice long way, but it's perfect. That means please make sure that you know this. Probably these formulas we will provide for you, but the notation, this is what we want. Yes, what I want my students to know. And I can just show you the short version of this question. If n is actually not infinity, if n is, for instance, finite number 4, x squared between 0 and 4, we have to estimate the area under the curve using just 4, only 4 subintervals. We're dividing by 4, we will go 1, 2, 3, delta x is 1, we can see, because we will divide 4 by 4, and value of the function for 1, value of the function for 2, value of the function for 3, and for 4. 1, 2, 3, 4. Function is x squared, 1 squared, 2 squared, 3 squared, 4 squared. We're adding, this is one rectangle, second, third, and the fourth. We don't need any sigma, we don't need any formulas, simply arithmetic. All of these rectangles, the area of the first one is 1, 4 of the second one, the area of the third one is 9, last one is 16. Okay, the area of these rectangles is 30. It's a little bit more than under the curve, but it's the approximation based on the condition. We may also do the left-hand side. I did the left-hand side. We can, oh, wait, and that's the right, that's the left. But the left one, we will have value for 0, value for 1, value for 3. We always end up with 1 before the last one. Adding all of those, and delta x is 1. Yes, delta x is b minus a divided by n, 4 over 4, 1. Okay, that means enjoy the approximation of the area under the curve using maybe just the finite number, small finite number of rectangles. That's the right-hand side, left-hand side, or infinitely many of them. Right? That's this is the approximation. That's integral, antiderivative. But we will put this notation, this definition in the next section. Thank you for this session. Thank you.